Hi, my name is Huayu Ge. I'm going to introduce the architecture of Xmon qubit based on the publication Coherent Josephson Qubit Suitable for Scalable Quantum Integrated Circuits by Barron and his colleagues. I would like to divide my overview of the Xmon qubit into 6 parts. The first part is motivation to build the Xmon qubit and the leading applications. Part 2 is the history of superconducting qubits. Part 3 focuses on the functions of the Xmon qubit. Part 4 looks at the advantages of Xmon qubit compared to other architectures, such as Transmon qubit, 3D Transmon, and Charge qubit. Part 5 cites 3 up-to-date reviews to show the state-of-the-art. Finally, Part 6 provides an outlook and summarizes the major challenges faced by Xmon qubit in growing dimensions. In short, developing the Xmon qubit is an attempt to build a quantum computer, or at least to get a little bit closer to that. Superconductivity provides an appealing platform because it allows for scalability. We can make quantum integrated circuits with many elements having individual control lines. However, quantum coherence in superconducting circuits is very vulnerable. Many factors can lead to decoherence, such as material defects, electron system excitations, and radioactive coupling to external wiring. To minimize these and other effects, researchers try to put qubits in 3-dimensional superconducting cavities. These 3D qubits show high coherence. For example, the energy relaxation times in 3D Transmon qubit is between 30 and 140 microseconds. Then why don't we just stick to the 3D Transmon qubit? Well, coherence is not the only thing that matters. To build a quantum computer, tunability and efficiency in fabrication and connection are also very important. The Xmon qubit seems to be a good choice under these criteria, as it allows the implementation of fast 2-qubit gates and has long coherence time. This is the motivation to build the Xmon qubit. And naturally, its leading application concerns the realization of chip-based quantum computer. From the historical perspective, the Xmon qubit is closely related to the Charge qubit and the Transmon qubit. In 1997, Schneemann first suggested the idea of superconducting Charge qubit. 10 years later, in 2007, Robert, Michael, Stephen, and their colleagues at Yale University developed the Transmon qubit, which is still a Charge qubit but with a large Josephson energy, EJ, to charging energy, EC ratio. Additional capacitors are used to reduce the charging energy. As discussed in lecture, this leads to a balance between the two effects: dispersion, that is sensitivity to charge noise, and the anharmonicity, that is qubit subspace isolation. The former decreases exponentially and the latter follows the weak power law. If you look at the fourth graph on the left, when EJ to EC ratio goes to 50, the exponential reduces to 1. In 2013, Barron and his colleagues designed the Xmon qubit based on planar Transmon qubit. Although there are some other differences, which we will discuss later, the Xmon qubit is like a grounded Transmon. The qubit is given the name Xmon because of the cross-shaped qubit capacitor. The 4 arms of the qubit capacitor connect to separate elements, each having a different function. On the top, there is a coplanar waveguide resonator for readouts. On the right, there is a quantum bus resonator to mediate coupling to other qubits. On the left, there is an XY control to excite the qubit states. And on the bottom, there is a Z control to tune the qubit frequency. The electrical circuit is equivalent to a grounded Transmon, with the capacitor in parallel with a tunable junction. Different from a traditional Transmon, the qubit capacitor is formed by intersecting 2 coplanar waveguide lines. The qubit capacitor connects at the bottom to the tunable Josephson junction, which is formed by the rectangular ring-shaped superconducting quantum interference device. The rectangular ring is intersected by 2 identically sized aluminum tunnel junctions, which is the blue regions. Among the 4 connections to the Qubit capacitor, 3 of them are based on a coupling capacitor. The XY control driveline is connected with a coupling capacitor of 60 autofarad, which allows the Qubit state to be excited in 10 nanoseconds. The estimated relaxation time T1 is 0.3 milliseconds. The Z control has a driveline that is galvanically connected to the superconducting quantum interference device. This forms an inductive coupling with a mutual inductance of 2.2 picohenry. The measured coupling between the Z line and the qubit has a T1 around 30 milliseconds. It's a good time to summarize the numerical results of the Xmon qubit. This architecture has a measured decay time T1 up to 44 microseconds. The ground to excited state transition frequency is about 6 GHz. The ratio of Josephson to charging energy is about 95. The high-power single-shot readout scheme results in a fidelity between 70% and 85%. The loaded quality factor Q is about 104, and the measurements were done with a base temperature of 30 millikelvin. I will address the advantages of the Xmon qubit based on how well it fulfills the target of building a surface-code quantum computer. The Xmon qubit has a long coherence time. In fact, the developers combined together 3 designs for high coherence. First, they used the molecular beam epitaxy aluminum as high-quality material. Second, they used coplanar waveguides, which have low radiative loss. Third, they embed the architecture on a ground plane and use the aluminum lines at the capacitor ends to tie the ground planes together. There is a table comparing the T1 and the T2 star value of the Xmon qubit to other planar superconducting aluminum qubits. Obviously, the Xmon qubit has advantages over most architectures in coherence time, and it is approaching the coherence of a 3D transmon qubit. The second advantage is the tunability. As mentioned earlier, 3 of the connections are made with a coupling capacitor, as the qubit is connected to the ground. An advantage of this approach is that each coupling can be individually tuned and optimized. This cannot be easily realized in other Josephson qubit architectures. Finally, the Xmon qubit enables fast control and at the same time preserves coherence. The XY control driveline allows the qubit state to be excited in 10 nanoseconds with nearly no effect on coherence. The Z control also allows the qubit to be rapidly tuned on the time scale of nanoseconds. Let's now look at the state-of-the-art of the Xmon architecture. Besides developing the Xmon qubit in 2013, in 2014, Behrens and his colleagues successfully achieved an average single qubit gate fidelity of 99.92% and a 2-qubit gate fidelity of 99.4% using Xmon qubits. On the right is the optical image and the circuit diagram of the experiment setup consisting of 5 Xmon qubits. In Figure A, the integrated Josephson quantum processor consists of aluminum, which is the dark part, on sapphire, which is the light part. The 5 cross-shaped devices, Q0 to Q4, are the Xmon qubits placed in a linear array. In Figure B, we can still easily recognize previously mentioned 4 parts in the circuit diagram, but this time 5 qubits are connected. We can see that the connectivity of the Xmon qubit makes direct nearest neighbor coupling of the qubits possible. We can drive individual qubits through XY and control the frequency through inductively coupled Z. Figure C is the schematic representation of the entangling operation using controlled phase gate with unitary representation UCZ. Teng Huiwang and his colleagues developed an alternative way to achieve high-fidelity quantum gate using Xmon qubits in 2018. They built a universal quantum gate using a shortcut to adiabaticity trajectory. Various single-qubit STA quantum gates are created through a precise microwave control, and a gate fidelity of 99.8% is achieved. The STA gate can also be extended to multi-qubit system and allow a large flexibility in the control parameters such as the pulse amplitude, operation time, and pulse shape. Also in 2018, Xue Guo and his colleagues investigated the ATS effect due to the quantized EM fields on the Xmon qubit circuit. They see the qubit energy level splitting when the cavity is resonantly coupled to the two upper levels of the qubit. This property may allow Xmon qubit to be used as a single photon switcher, or rather in a quantum network. On the right is a schematic diagram of the setup. The green line is used for applying a microwave field to drive the coplanar waveguide resonator, and the red line is used for adjusting the energy level of the Xmon. The black line is connected to the transmission line for detection. Do you still remember the achieved single qubit gate fidelity we discussed in the previous slides? Yes, it's 99.92%. However, the fault tolerance threshold for the surface code error correction is just 99%, which means the Josephson quantum computing based on Xmon qubits is already within the fault tolerance range. This progress brings us closer to the realization of a quantum computer and shows us a clear path to create large-scale, fault-tolerant quantum circuits. Based on the Xmon array used in the Barron's experiment, the next step is to extend the length of the array, or to generate a two-dimensional grid of qubits. However, scaling up in either directions is very challenging. Although at the beginning of the video, we say superconducting circuits allow for scalability, we are still facing a big trouble when the architecture grows in dimension. It is hard to preserve the long coherence and remain in the fault tolerance range after adding more qubits and wires. Unfortunately, the alternative approach to achieve high-fidelity quantum gates based on the STA trajectory is facing the same problem. An ideal adiabatic operation means slow speed. Slow speed means long operation time, which means difficult to scale up. The scalability will remain a big engineering challenge for future development of large-scale Xmon architectures. Another challenge is the need to improve coherence. Fortunately, this is a tractable challenge because of the recently discovered coherence property of titanium nitride. Combining Xmon geometries with titanium nitride is a realistic idea and may lead to a longer coherence in the future. This is the end of my video, and thank you for watching.